So today we're going to talk about the ideal gas law. The ideal gas law is taking into account Boyle's, Charles, Gay-Lussac's, and Avogadro's laws and combining them into one statement. Well, how does that happen? So here's kind of a rundown of how we get this equation, PV equals nRT, in a short, abbreviated version. One, we start with the combined gas law. This statement sets these equal to each other. 2, 2, and 2. We can rewrite this statement so we no longer have our second P2, V2, and T2. We can set it as a constant K. Once we set it as a constant K, we also know that we have some other constants that are variable. We know that T, P, and V can be experimental, but we can also have a specific constant, and that's what we don't take into account in their equations, and that is the gas itself. When we take the gas into account, we have a couple things. This K now becomes the moles of gas versus the R. The R is equal to the pressure, volume, temperature, and moles. That would equal this. When we combine these together, we get the nice equation, PV equals nRT. So let's talk about R for a little bit, because R is a constant that doesn't change. R is variable. We always have to have a couple things present. One, the volume of units is always in liters. We cannot use milliliters or any other volume. It has to be liters. Temperature is still always in Kelvin. That makes sense. It's been in Kelvin. Moles is always in, moles. But the pressure can change. The pressure is what is going to change our numeric value for these. Just remember that 1 atm is equal to 101.3 kPa, which is equal to 760 mmHg. These are all equivalent to each other, which makes sense that the R value would change based on that. That's a little information that we have to know in order to start doing these problems. So why do we use the ideal gas law? Well, in the real world, we know that the ideal gas law, by the way, doesn't really happen in real life, but a few things are always going to happen. We know the proportions, the indirect and direct relationships are always the same. The only thing that really does change in the ideal gas law is going to be the particles themselves. The intermolecular forces, we can't change. But everything else stays in the same proportion as it always does. It behaves the same way. And so even though there is really no true ideal gas, the particles will behave in a manner that should represent a very close relationship to the ideal gas law. So it does make sense to use it. It's kind of like our theoretical yield for this. All right, let's start with this. So it says if the pressure exerted by a gas is 25 degrees Celsius at a volume of 0.044 liters and is at 3.81 atm, how many moles of gas are present? Remember, we don't need to know the type of gas in this situation. We just need to know what we have. So here's what we do know. So our temperature is 25 degrees Celsius. We have to add 273 to get Kelvin, which gives us 298 Kelvin. We have our pressure at 3.81 atm. Remember, I said atm is important. That gives us our R value. Our R value is 0.0821. You might want to have this for the test. Super important that we know those R values. I don't expect you to memorize them. We also have a volume of 0.044 liters, and we're solving for our moles. In this way, we rework the equation so N is equal to PV over RT. Putting our pressure of 3.81 in, timesing our 0.044 liters. Then we divide by our 298 Kelvin and an R value of 0.0821. Again, our R value comes from this table. Our moles in this case is going to be 6.85 times 10 to the negative 3 moles. Again, we don't need to know the type of gas we have. It's all relevant here. So let's calculate another one. Calculate the volume if you have a 0.32 mole sample of a gas that occupies 265 Kelvin at a pressure of 0.9 atm. So they do give us our pressure of 0.9 atm. Super important because now we know our R value is 0.0821. They were kind enough to give us our temperature in Kelvin, so we don't have to convert that. And our N is 0.323 moles. Our volume label will be liters, and it's what we're solving for. So when we rework PV equals nRT, we get V is equal to nRT divided by P, giving us the numeric value of 0.323 times 265 times 0.0821. Remember, if we put this in the calculator, please use parentheses, all divided by a pressure of 0.9 atm. When we solve for this, we should get a volume of 7.81 liters. Really important to understand that we're still looking for that volume, and it has to be in liters because if we refer back to that equation, our volume constant is always in liters. This is kind of a neat equation that we're going to use right here. We remember from way back in chapter 2, density is equal to grams per liter. And M is our molar mass, grams per mole. Because PV equals nRT is dealing with volume and moles, we can actually rewrite that equation because now grams cancels out to reflect the density, which is pretty neat if you think about it. So we're going to use the equation density is equal to the molar mass times pressure divided by our constant R and temperature. So let's try working through one of these equations. We are given what is the molar mass of a sample of gas that has a density of 0.9 grams per liter at 1.0 atms of pressure and 25 degrees Celsius. So we are given the density of 0.9 grams per mole. We are looking for our molar mass, which would again be, the density should be, I have the wrong label, grams per liter. This one is grams per mole. And we are given a pressure of 1.02 atm. Again, really important that we know that because that gives us our R value of 0.0821. And then we have a temperature of 25 degrees Celsius, which we know we have to add 273 to get our Kelvin temperature of 298 Kelvin. Again, using the equation, density is equal to the molar mass times pressure divided by RT, we can rework this equation to get the molar mass is equal to the density times the R value times the temperature divided by our pressure, giving us 1.09 times 0.0821 times 298, all divided by a pressure of 1.2 atm. Our molar mass in this case is 26.1 grams per mole. Now it doesn't tell us what the sample is, so we're going to assume it's probably not an elemental because all gases are diatomic. So to use this 28.6 would be kind of hard unless we know what kind of gas we're dealing with. However, in the next problem, it actually tells us. It says calculate the grams of nitrogen gas present in 0.6 liters if the sample is kept at a pressure of 1 atm and a temperature of 22 degrees. So let's see what they gave us in this equation. They gave us a volume of 0.6 liters, a pressure of 1 atm, which means we have an R value of 0.0821, and a temperature of 22 degrees plus 273 to get a Kelvin temperature of 295 Kelvin. In this case, we still want to use the equation PV equals nRT, and we want to solve for moles because we already know how to convert grams into moles by using the molar mass conversion. So N is going to be set equal to PV over RT, giving us a volume of 0.6 liters times 1 atm, all divided by our constant R of 0.0821 and a temperature of 295 Kelvin. Our N in this case is 0.0248 moles, and we know nitrogen gas is a diatomic as N2. But we're not finished quite yet because it said, how many grams do we have? We know how to do a molar mass conversion starting with the moles of N2. We know 1 mole is equal to the molar mass of 28 grams of N2. 14 is the molar mass of nitrogen multiplied by 2. We solve and we get 0.694 grams of nitrogen gas. Now remember, the ideal gas law doesn't happen in a perfect world, but this value would be pretty darn close, depending on the intermolecular forces attraction to one another and the container in which they're placed in. So it really would tell us the mass of the nitrogen that we would have. It would be pretty accurate. We might have a percent error of less than 5%, which is pretty consistent, I feel. So, big reminder, this table is super important for solving because this numeric value changes based on pressure. Volume must stay in liters, temperature must stay in Kelvin, and molar mass stays in moles. Thanks, and that's the ideal gas law.